Hello everyone. Thank you for joining my session today. I hope you've been enjoying the rest of the Azure Community Conference so far. My name is Cecil Phillip and I'm a cloud developer advocate at Microsoft. And in this session, what I want to do is talk to you about some distributing messaging patterns that you can make use of inside of your applications today. Now, I'm going to be using .NET to kind of drive some of these demos, but these patterns really have nothing to do with .NET. They should be able to be used whether you're using a mixture of different programming languages like .NET and Java and Python, or even just using one set of languages to build your applications. Also, I want to say these patterns have nothing to do with hosting in the cloud. If you are hosting in the cloud, then sure, there'll definitely be some benefit there. But also, if you're running your infrastructure on premise, if you're running them on VMs or you're running them on your local infrastructure, well, that should be fine too. And you should be able to find some value in one or more of these patterns that I'm about to show you. So why don't we go ahead and get started and see what this is all about. Now, the first thing I like to talk about whenever we try and figure out, well, how do we move information between these different systems? How do we move information between the different parts of our applications that are spread across our infrastructure? And I think there's three main ways that we could do that. And the first approach I'd like to talk about is the direct approach, where we can move messages between two very well-known endpoints. So that means that these two different parts of our system know exactly who each other are, they know where they're located, and they'll use some type of address to say, hey, I need to communicate with this thing, or I need to send a message over there. And this is a fairly common scenario. You could think about it like making a request using a web API or using something like, Twilio or the Cognitive Services API to make a request for some information, and then you'll wait for your response. Another scenario or another approach that we talk about is the brokered approach, where we'll have some intermediary that'll be in control of distributing the messages to wherever it needs to go. Again, think about something like a message queue, where I'm going to send a message into something like Azure Service Bus or RabbitMQ. And then that job of the broker will be able to inspect that message, look at the different metadata that's associated with that message, and determine where the actual destination of that needs to go to. And then we'll see another approach where we broadcast messages over to a set of interesting parties. So in this scenario, the creator of the message or the source of the message is going to essentially say, hey, anyone that's interested in knowing about this topic, here you go, here's the message, right? But it doesn't know who's listening, it doesn't know where they are or where they're located, and also doesn't know what it's going to do with that information that you've just shared. But the only important part is that the subscribers, the other side, is going to be able to listen and say, okay, something important is happening. Now I'll grab that message from the source and we'll do some work with it. So messaging is really all about getting data from one part to another, right? Going from system A to system B, from point A to point B. But there's some things that we need to consider whenever we're moving messages back and forth, because it's never usually that simple. Sometimes there's a lot of senders on one side sending messages over to the other side, right? And so we need to think about, well, how do we deal with those types of scenarios? Also, we have a situation where, a lot of data needs to be sent over that pipe, right? And so how do we efficiently handle all of that information that we want to send over the network, over the wire? And then sometimes we, might have just a few senders, but we have a lot of receivers, right? And now we have to figure out, well, how do these receivers compete for that information? Which one are we going to send that message to? And how do we know what's over there? And how do we know which ones are still healthy and being able to process our work? And then sometimes on the other side, we not only have a lot of messages, but we have a lot of different types of messages. And we need to know which receiver is the one that actually needs to know about it, which one needs to be able to process it, right? And then moving on, sometimes there actually isn't anyone on the other side listening. Right? So you might want to send a message, but no one's actually there to receive it, right? We need to be able to handle that scenario as well. And then for anyone that's ever written a network application before, sometimes bad things happen. And sometimes when we're sending the message over, sometimes the network fails, or maybe even the thing that's processing the work is down and it's failing, right? We need to be able to handle what we call transient errors whenever we're sending our work over, so we make sure that that work is not lost in transit. And there might be times where the receiver, right, the processor or the thing that's taking in these messages, it's really busy. And now it might take longer than usual for our work to get processed. We need to be able to handle those scenarios in a really elegant way so that it doesn't affect the way that our business continues to run. Now, as we try and handle these scenarios inside of our applications, it's very important that we understand what's the underlying protocol that we're using and what are some of the features of that protocol that we can make use of as we're building these distributed systems. And these open protocols are what are going to give us the flexibility to not only handle these different types of messaging scenarios and failures, but also it's important that they're open so that we could plug different implementations of them on one side or the other, either on the sender side or the receiver side. So that means that regardless of whatever server I'm using, like my client should be able to talk to it or message it. Think about the case of when we're using something like HTTPS and WebSockets, right? Regardless of whether you're using Nginx or Apache or Kestrel, or maybe you're even using like a reverse proxy like Envoy that understands HTTP, any HTTP client should be able to send a message over and get a response back. Because again, that is a very well-known protocol. It's something that's tested and something that we have expectations about how it works. Right? We talk about the body of the message and the headers of the message, right? Like all these things are very well known. So it really shouldn't matter about the implementation per se, but it just matters that we're using like a very well-known protocol to send those messages back and forth. The same thing too when we talk about messaging with AMQP. AMQP is really popular and there's a lot of implementations across things like ActiveMQ, RabbitMQ, Azure Service Bus, and tons of different other options, right? And this will allow us to do that brokered messaging pattern, and we'll see a little bit more of that as we go on, right? But again, this uses a very common protocol, so there's different expectations and different implementations. So as we swap clients and servers, I should be able to send the same message, assuming that I'm using the same version of the protocol, and I shouldn't have to change my code too much to be able to do that. Another protocol you might see coming up a lot lately is MQTT. And this is used a lot in IoT type scenarios for low powered devices that need to be able to send messages really quickly from wherever they are. And again, like there's tons of implementations of these, whether we're talking about ActiveMQ, RabbitMQ, and tons of others that we can make use of. Now, I want to break down these patterns into two different categories, right? Synchronous and asynchronous communication. Now, when we think about synchronous communication, we have a sender and a receiver, and the sender is going to send a request and it's going to wait for an immediate response, right? So it's not going to fire and forget it. It's not going to send the message and walk away. It's going to expect that request to be handled by a receiver and a response to come back fairly quickly. So essentially the sender is going to block or it's going to wait there until it's being able to get some answer from where it sent the message. And then we also have asynchronous communication, where the sender is going to send a message, but then it can move on to do other things within its timeline, right, within its workflow. And this usually makes use of something like a broker or some type of intermediary to be able to go and handle that message and the delivery of that message. But the great thing about that scenario too, though, is that the sender really doesn't need to know where the receiver is. It can actually just send the message, and the only thing it needs to know about is that broker part that's in the middle that's going to be able to distribute the message. But it knows nothing about the receivers. It knows nothing about what it's going to do with the message. It knows nothing about where it's located. And so then we have a really interesting decoupling there as an option for sending messages over. Now let's move forward and start talking about some of the synchronous messaging patterns that we could start using. Now, I'm sure a lot of us are already familiar with things like HTTP and making web requests and using HTTP client and those types of things. So what I want to do instead is talk a little bit more about what are some of the things that could go wrong in using a synchronous messaging pattern like that, and how can some of these patterns solve some of those types of issues. So the first thing I want to talk about is throttling. Now, in this scenario, you might have a server or you might have a single application on the right side, as you can see here, that is sitting down and it's waiting to accept messages. But on the left side, I might have a lot of different clients that are very chatty and they're sending messages at a very high rate. And what could happen, if you remember one of the slides I showed before, is that the server can become really overwhelmed, right? It could, because there's only so many servers here and there's way more clients, now it starts to take longer to receive the message. It might even start, dropping messages, and it's not able to process it at the rate that it needs to, not in a reliable way. And so implementing throttling could really help the server, one, identify like which ones of these clients are the chatty ones and sending messages really quickly, but also slow down the rate at which it's processing those messages, so that now instead, the client can know, hey, well, I'm sending messages too fast, I need to slow down. Or, the server is not ready yet to accept any more work. I need to have some type of back off strategy that I can implement to say, okay, well, maybe I'll try it again later, or maybe I'll wait for 5 minutes or 2 minutes or whatever the case is. Another really interesting pattern that we can make use of in this synchronous messaging world is the use of something called a reverse proxy. What's really interesting about that is, if you notice on the right side, now I can start to scale out the amount of servers that I have. But if I start scaling out the amount of servers, well, how do my clients know what servers are available? Does that mean that they're going to have to keep an address list of all the available servers? And, what happens when a server fails or a new one gets stood up? Like, how does it know that there's been a change in the number that's available inside of it? And this is one of the benefits of using something like a reverse proxy. And that is, the clients now, like the senders or the originators of that message, of that work, only need to know about the proxy. And then the proxy knows about the health and the status of all these other available servers that exist in the background. So what's really great now is that the clients now can send messages, send their work over to the proxy, and then the proxy will use some type of routing strategy, some type of distribution strategy to pick an available server that's maybe not too busy or haven't gotten work in a long time, to be able to process that work and send it back over to the client. But from the perspective of the client, again, we're not changing any code. And instead, we're just giving it the address of the proxy that will forward on the message and then send it all the way back. Another great thing about the proxy is that we can also enhance it with some additional functionality. So maybe you have something like caching or some additional logging or some additional security concerns that you need to have implemented. And instead of copying that and having it implemented on every single server, instead what you could do is implement it on the proxy that's existing in the front. And now we have a somewhat centralized place to have some of that, some of that set up. But then also that server code that's on the other side becomes a little bit less complicated. And that means it's a little bit less for you to have to maintain. Now, we just talked a lot about what we can do on the server side, but there's some things that we can do on the client side as well, right? If we take a look at the diagram, we might have situations where, like we showed before, the server might be busy, the network might be unreliable, we might lose connectivity at some point in time. But still, we don't want to lose the work that we want to get processed. And so now we can implement what are called retry strategies on the client. And what's really interesting about this is that we could use that underlying protocol that we spoke about, right? So in this case, let's say we're using HTTP, and, based on what's happening, let's say the server sends a message back to say, hey, you're sending messages too fast, you need to slow down. The client can look inside of that header, right? It can inspect the metadata of that message and say, oh, okay, well, the server said I should slow down. I'll try again in 5 minutes. But like that information is coming back from the server inside of its response. We also might have situations where, like I mentioned before, like the actual connectivity might not be available. The network might drop, might lose Wi-Fi signal or something of that sort. Then the client needs to know, oh, wow, like something happened. It's not the fault of the server, but it's just the fact that we have an unreliable network. Sometimes I need to resend the message, right? And then again, you'll have some type of intelligent strategy that you can implement on the client to be able to handle those scenarios. All right, so I think we've spoken enough. Why don't we head over and take a look at some demos, and I could show you how we could do some of these types of things using .NET. So let's head over to Visual Studio Code, and I could show you some code that I've written around this. Now, I have two projects here that I want us to focus on right now. One is just like an API, and regular HTTP API, and another one is actually a worker service that's going to be able to generate load that runs against that HTTP API. So what I'm going to do now is I'm going to do, inside of the terminal, you see I'll do a .NET run, .NET run /p. So all I'm going to do is I'm going to execute that project that's inside of here. And now soon from now, you'll see like my API is going to get started. And I'll go ahead and open another window really quickly as well. And inside of this window, we're going to go ahead and we're going to also get ready to run that. We're going to get ready to run that client as well. So this is going to be .NET run. I'm going to do a -p for this one, and this is going to be HTTP client items worker. I'm not going to run this one yet, but I do want you to see some behavior that you'll notice from the API. Now, I'm going to copy the address here that you can see where it's working. And over here in Postman, notice that I have the address here already ready to go. Now, when I send a message over to that API, I should just expect some results to come back, right? Like nothing crazy or special there, right? So there's my response back in JSON. But what I want to do is I'm going to keep sending messages over and over and over again. I'm going to keep hammering the server. And you'll notice sometimes I get this message back, right? And the message says, API call quota exceeded. So that means that I'm sending too many messages to the server within a given time period. So now my API has implemented some level of throttling. It's telling my client, hey, you're going too quickly. You need to slow down because I'm not going to be able to process these messages at the rate at which you're sending them. And if we come over here and we take a look at the headers for the response, you could also see as we look through some of these keys, we're also getting a retry after inside of here, right? So what the retry after does is it indicates, well, you can send another request after so many seconds. And this one is saying I could retry after 1 second. Also notice too that I'm getting an HTTP 429, right? Like that's a very common status code to use whenever you're being throttled. And you may or may not have seen that when you're using some third-party services, but you can implement it inside of your own applications as well. All right, so let's head back over to the code, and I can show you what my API looks like. So if you're familiar with .NET, what you'll notice here is that I have an API controller. I'll close this so it gets out of the way. But nothing special is inside of my controller, really. I'm getting some data, and then I'm just returning the result, right? And I have two methods that are doing that. But like I mentioned before, my API does implement throttling. And I'm using a package called ASP.NET Core Rate Limiting to be able to specify some of those things. Now, here inside of my code, in between lines 49 and 53, this is where I'm setting up inside of my application, I'm enabling like that throttling feature, right? So I have a few components in here that, calculate the counts, or they maintain a certain count for the client. And then also I have some components that are concerned about the policy, right? The policy being, well, what's the configuration for the rate limiting? Like how many requests can I send per second for a given client? Now, let's take a look at our configuration file. This application uses a JSON configuration file. And you'll see here on line 29, right, I have something in here called client rate limiting, right? This is just a configuration section in here. But also, if we take a look at the part that says general rules, you can see that's where I'm letting it know, well, what's those policies, right? Like what are the way that I want this thing to be able to limit requests on a client by client basis. And you can see here, this is saying, well, the first rule says for any endpoint, so that means that for any HTTP path that's in my application, I only want you to be able to send 1 request per second, right? And then the second rule is saying, well, you can also send 100 per minute if you wanted to. And again, you can have multiple rules, but then you can also have rules that are very specific to certain clients as well, right? So you have the option to kind of configure this and make this work however you want it to, right? And like I said before, like we're using the power of HTTP to send that information back over using the headers, right? Which is really important. Now, what I'm going to do is I'm going to go ahead and run this worker, right? Now, my worker is going to go ahead and kick off. And one of the things that my worker does is it's going to like batch set a lot of requests at the same time. I'm actually going to make this window a little bit bigger so you can see what's happening. But what you'll notice is every few seconds, like this, it spins up. And then like I'll scroll up and I'll highlight one of these messages for you. You can see here it says like request number 7, attempt number 7, attempt number 8, so on and so forth. And it's going to keep retrying over and over and over again until eventually we get to the point that all of my requests have been sent, right? So in the beginning, I just tried to send 10 requests super fast. And the server said, nope, too much, you got to slow down. But then my client was able to look at it and say, okay, I'm going to try again, but I'm going to try these other requests in so many seconds. Now, let's take a look at our client and see how exactly this is implemented. Now, this is a .NET application, like I mentioned before, and this code is, not tremendously complicated, but what you're seeing here inside of this section is this is where I, spin up my client, but then this is also where I'm saying, hey, I just want you to, continue sending a lot of requests to this /API items endpoint. And if I take a look at my program.cs file, right? So I'm using the HTTP client inside of my application, but I'm also using a package called Poly. And Poly is a really great resiliency framework that will allow you to implement different, resiliency patterns, like being able to do retries and circuit breakers and some of those types of things. So inside of my code, you'll see on line 65, I'm creating a policy that says whenever I have a status code of 429, so whenever the server says, hey, you're sending too many requests, I want you to go ahead and retry it. But how is he going to know how much to retry for? Well, like I mentioned before, we're going to use the protocol, right? We're going to take a look at what's inside of that HTTP header. So notice there on line, that looks like 969, I'm going to say, well, let me get the value of the retry header if it's available. And then I'm going to use that to say, well, hey, I'm going to retry after these seconds. And if it's not there, I have my own defaults that I'm going to use instead, which is fine. And then at the bottom, like that little section that you see from line 76 down to line 80, that's just me doing some logging, right? Like I'm just, setting some logs over to say, well, this is what's this is what's actually been happening. But that's it, right? And so that's what you can do to start implementing some of those retry strategies and also some of those throttling strategies inside of your application. All right, let's head back over to the slides and we can start talking about some asynchronous patterns. Now, if you recall from earlier in our conversation when we talked about asynchronous patterns, in this model, what we have is a case where we have a sender and receiver, but the sender is going to send a message, but it's not going to wait on the receiver to respond immediately. It's able to pass on that message and continue doing its work, which is, very opposite to what happens with the synchronous patterns. So let's start talking about some of these patterns that are here, some very common patterns. One of the most common ones is a situation where you may have some long running work that you have to execute. And let's say that work might take, minutes long or hours long, or sometimes it might even take days for that work to get completed. Now, if we're using something like HTTP or, something that uses a synchronous pattern, it's not reasonable for us to expect that connection to be held open for minutes or hours or days while that work is being processed, right? Like now you're just taking up system resources, and that's a very efficient way to get work done. A better pattern is to use something like a queue or a broker in the middle. And what's great about this type of scenario is that the source, the producer, right, the origin, the thing that actually creates the message, can pass a message on over to the queue, and then it could just move on with life, right, and do whatever else it wants to do. Right? It doesn't have to wait for a response in that moment. And instead now the consumer on the other side, at its own leisure, can pick up those messages whenever it needs to. And then work can happen. And, if there's errors on the consumer side, because, the consumer has to communicate with the queue, the consumer can implement its own retry policies to pull that message out and start processing it. And then the producer on its side, again, it could go ahead and continue doing whatever it was doing before. And they don't have to know anything about each other. They don't know where each other are. They don't have to be implemented in the same programming language. And they may even be like different versions of them as we kind of move on. If we do have a scenario where the producer does need to have a response back, we could still do this in a very asynchronous way. Again, and using the underlying protocol, maybe something like AMQP 1.0, we could use that metadata associated with the message to specify what's called a reply queue. So in a scenario where I send a message over and I do need a response back, but I could wait for it, I could get it sometime later on, I'll specify a response queue or a reply queue, and then the consumer, after it's finished processing that message, will send it over to the reply queue, and then my producer will get notified that there's a message there and it can pull it out and, do whatever it is that needs to happen at that point. There's also scenarios for handling the bad path, right? Like the unhappy path. What happens if a problem happens with processing the message? And in this case, on the consumer side, we can put it in something known as the dead letter queue, right? And this is a fairly well-known pattern too with a lot of different messaging systems. And inside of the dead letter queue, this essentially is a separate space for things that weren't able to get worked on or processed. And now inside of here, we could, implement some type of policy that's going to email someone or reach out to, some different folks in the company, or, trigger some type of different workflow to be able to handle the work that we saw problems with. Now, building on top of that past pattern, another thing that we could do is implement something called load leveling. So with load leveling, notice on one side, we may have just a few consumers or maybe even just one consumer. And on the other side, we have a lot of producers. Now, if you remember using the synchronous pattern, we had to do something like implement throttling because the one consumer or not enough consumers can't handle like a whole lot of producers. Well, using a queue in the middle, you almost kind of get this by default, because regardless of how many ever producers are here, right? Like messages are able to be sent and each of those producers are able to go on and continue doing the work that they want to do. But then also on the other side, the consumer could just pull messages out at its own rate. And even though like the more messages that are there, it's probably going to mean that the longer the consumer is going to take to get to each individual one, it's never going to be a situation where anything is being blocked, right? Like the producer shouldn't be being blocked because it's able to send the message and move on. And then the consumer is not blocked because it's not tied to any producer, which is a great way for us to, again, like decouple our systems, one, and then two, not really put too much stress or strain on the resources that we're making use of. But now, what happens if we're in a situation where, okay, well, we do have the consumers pulling things at their own rate, but we do need them to pull more faster. Well, one of the things that we could do is we could just add more consumers, which is great. And just like before, inside of this type of architecture, inside of this type of system, the producer doesn't know how many consumers there are. The consumers don't know how many producers there are. The only thing they know about is that, there's that queue in the middle that work can be sent into and pulled out from. And now as we add more consumers to the system, then we're able to process those messages at a faster rate. And one of the interesting things that can happen here too is that, we can have some type of intelligent scaler, some intelligent scaling can happen on the consumer side. So let's say the producers are, we have so many producers, but they're sending messages, relatively slowly, and we can get away with like one or two consumers. But then maybe something happens, maybe, there's a sale, it's, big holiday and a lot of folks will start shopping. But now we're getting requests for work coming in a lot faster than they usually do. Now, what can happen, maybe we have something in our system that says, hey, the length of the queue has increased exponentially, or messages are coming in at a faster rate, right? We can do some type of math to determine, well, okay, well, I'm going to add another consumer. I'm going to add another one. I'm going to add another one until the queue length is down to something that's we consider to be reasonable, whatever your personal threshold for that might happen to be, right? But like I said before, we don't want to do this ourselves, right? We want this to be somewhat of an automated process, right? And we could write some code that'll be able to do that for you. Another thing for us to think about when we look at the asynchronous messaging patterns is how we can do something called publish and subscribe. So remember when I was talking about broadcasting a little bit earlier today, we have scenarios where I just want to send a message out and whoever cares about it has the ability to get a copy of that message and inspect it, right? Which is great. So in this scenario, I can have a producer send a message over to something called like a topic, and each consumer could get a copy of that same message once they're listening or subscribed to that particular topic. Not only that, let's say I might have a topic, but like each topic has a different criteria. So let's say, I'm publishing something about cars. Maybe consumer one only cares about red cars and consumer two only cares about blue cars. Maybe consumer three cares about red and blue cars. And in that type of scenario, now we can implement a filter so that now, even though each consumer can get a copy of every message, they might not want to do that. They might only want to get copies of messages that they care about. And so now I'm able to implement a filter that'll only give me like those interesting messages to me. And now using whatever my specific business logic is, I can handle those messages that are important to me. Another scenario that we want to make sure we're able to handle when we're building these distributed systems, and particularly when we're doing asynchronous messaging, is, how do we handle scenarios where the network goes down? Right? It's commonly known that, as you're building distributed systems, you can't trust the network. At some point in time, the network can fail, things happen. You might lose power. You might have a brief moment of loss of connectivity, but then you don't want to lose your work, right? Your work is very valuable and important to you. Now, how can we continue to send these messages and make sure that they don't get lost, even though we may not have connection to that broker that may exist on another network, on another computer? Maybe your producer, is an IoT device that's on premises, and then you're using a queue that's in the cloud. Like, how can I talk to that thing or not lose those messages when I do have interruptions in connectivity? And one interesting pattern that I'm really love to show you is how we can make use of an intermediary broker. And so what happens in this type of scenario is, hey, our producer might be trying to get to Azure Service Bus that's in the cloud, it's hosted on Azure, but we can't get to it because of security reasons or the network is down. Well, instead, what we could do is we could push to a local queue, something that's either on the same machine or on the same network, and something that we have a little bit more control of in terms of access. And now at some point in the future, like that queue, that broker that has that queue can send that message over to the other one. So it's kind of almost like a store and forward type approach, right? Like this only purpose of this queue is to hold messages and send it over into other brokers, into other queues. And now on the other side, we can have a consumer that, whether maybe this might be our consumer, or it could even be a consumer from another company that has access to that other queue. But again, like this exists in another system and another network somewhere, and they have the ability to pull that. And again, just like before, the producer and the consumer know nothing about each other. We don't know where they are or how many of them exist. But the only thing that matters now is that I don't lose the work that I'm trying to push because of loss of connectivity, right? Like I have this queue that's able to add that extra level of resiliency for me. And so I have a lot more confidence and faith that my work is not going to get lost as we have like these little issues. Okay, enough said. Let's head back over to Visual Studio Code and let's look at demos of all of these different types of things so you can see firsthand what it looks like to implement them. All right, so now we're back over in Visual Studio Code, and I want to show you a different application that I have that is listening to a queue that's inside of Azure Service Bus. Now, let's take a look at this thing called the load generator, right? So the load generator, it is just a simple app. I'm going to go ahead and run it while we're talking about it. The load generator is just a simple app that, as you can imagine, it generates load, right? So what it'll do is it'll continuously add messages to Azure Service Bus that I have running in the cloud. But one of the things you'll notice here is that it'll start off with 5 messages, and then it'll go to 13 messages, and then it's going to jump up again to 19 messages. So every time it goes around in the loop, after some delay, it's going to keep adding more and more messages to my queue, right? And so I'm going to go ahead and let that run for a little bit. And what I'll do now is I will spin up another instance over here. And instead of just running the load processor, right? Instead of running the load generator, I'm going to run the load processor, right? So I'm going to do a .NET run load processor, right? And I'm going to go ahead and let that spin around for a little bit. And now what this should do is this should detect, there you go, you're going to see this thing kind of go crazy a little bit. But what this will do is it'll go ahead and it'll look inside of that queue and it'll start pulling these messages out. Let's head over to the Azure portal really quickly. And I want to show you what this actually looks like from a messaging perspective. Now, this is my Azure Service Bus instance I have running in the cloud, and I preset this up for this demo. I'm going to hit on the queues that you see on the bottom left, and then I'm going to hit the load queue, right? And this is the thing that I have here that's, receiving these messages. And I also have it, sending messages as well. Notice right now it says there's 412 messages in here. If I refresh this, you should notice that, over time, this number is just going to keep going up and up and up. And remember, that's because even though I have my queue in the middle, my producer is sending messages faster than my consumer can consume them. So actually what I need to do is I need to kind of come in here and add another one, right? I need to add more things to be able to process these messages, because if not, it's going to get a little bit out of hand. Notice here I refreshed again. It's already back up to 600. So what I'll do, I'm in VS Code, so what I'll do is I'll split the terminal here a little bit, and then I'll just add more instances of that same processor, right? Because, that should be able to help me deal with that a little bit. So just like I did before, I'm going to do a .NET run load processor. I'm going to run it here, and I'm going to do it here as well. So .NET run load processor. But now I have more things that are in here to pull those messages out. So I'm hoping if we head back over to this thing, oh wow, I'm all the way up at 700. But notice as I keep refreshing this, hopefully this should keep going down lower and lower and lower. Yeah, like notice the number is slowly starting to get lower, as we're, we have more things that are processing those messages, right? I'm going to go ahead and stop this because I don't want it to, look, I'm all the way at like 192 messages. I don't want to put too many messages in there. But I'm going to go ahead and stop this. But I do want to show you what the actual code looks like to run this, because if you're familiar with using Azure Service Bus, you might be surprised how little code there actually is in here. So this one is my load generator. And if I move this out of the way a little bit, the main section of code that we're talking about is right here, right? And essentially what I'm doing is I'm just like generating a random message, right? This is the payload, and we're going to serialize that payload into JSON. And then I'm going to create a new service bus message, and then I'm just going to call send. And very similarly, if we take a look at the processor, right? This is all the code here that's inside of the processor between lines 30 and 39, right? I'm using like the async enumerable support that's now in C# to do async streams. And I'm, asynchronously for eaching over the queue, which I think is a really nice pattern, and also makes my code a little bit easier to grok too. But most of the code here you see here too is also just logging, right? So I receive that message and then I mark it as complete, and then I just continue going, and I wait for the next one to kind of pop up, which is great. Now, one of the good things is that, like I mentioned before, I'm able to just spin up more of these things, and it looks like this is finished, so I could close these down. But one of the things there is that, as much as I could just spin up more instances of them, I don't really need to change any of my code, right? Like, which is a great thing. Like, it doesn't need to do anything special inside of my actual application. But one of the bad things that you might have noticed is that, well, I had to manually start them myself, which is probably not what I want to do. It would be great if I could come in here inside of Azure or inside of whatever infrastructure you're using and set up some type of process that'll do it for me. And there's actually an option here. If we scroll down to the left side under monitoring, there's this thing here called alerts, which is really interesting. So now I can actually create a new alert, and this alert will be associated with my messaging pattern service bus instance. And now I could, create some alerting rules around how I want it to handle when certain things happen in my queue. So what I'm going to do here is I'm going to select, count of queue or topic. And I'm going to say, I want you to take a look at the load queue because that's the queue that we've been using. So notice I just selected from entity name. And then whenever the count, because that's what we're looking at, is greater than 10, right? And then I want you to check it, I want to check it every minute, just for the sake of the demo. You could make that be whatever you want. Whenever that happens every minute, like I want you to do something. I want you to do some work, right? So we picked the service bus instance we wanted to look at. We picked the condition. Now the next thing that we need to do is say, well, what's the action? What's the thing I want you to do after the alert is fired? And we have a couple of options here as well. What I can do is create what's called an action group. And you notice I just clicked that action group option inside of that section. And you can fill out some of these details, but the important part here is the actions of the action group. And here I could select an action type, and I might want to run something that's like a logic app or message a webhook. And in this case, I want to use Azure Functions. And inside of my Azure Functions, notice it pops up this other blade on the right side. I can select a function that I already have. It already found this for me because it's in the same resource group in the cloud. But I can select an Azure function. I can select a serverless function that I already have running in the cloud to have it send messages to, right? And now every time this alert runs, it's going to go ahead and fire off my Azure function. Now I'm not going to run this because it'll take a little while, but I definitely recommend you go ahead and checking these out because this is a great way for you to maybe inside of your Azure function, you could write some interesting code to be able to look at that message that comes in, look at the condition, and then determine, okay, well, I need to create more instances. And then you could use the management APIs with something like, Azure container instances or something like that to say, hey, I want you to spin up another thing to start, consuming these messages a little bit faster. So that's great. All right. Now, the next thing I want to move on, let's talk about publish subscribe and that publish subscribe option that we mentioned a little bit earlier. So with publish subscribe, I'm able to send messages to a queue or to a thing, but then anyone that's interested in it could be able to get a copy. So with the ones that we've seen before, the messages have still been fairly one-to-one. So the first consumer that gets it is the one that continues to work with the message, right? All of the consumers don't get copies of the message. But when we run in a publish subscribe type of pattern, then everyone that's interested will get a copy of the same message. So that might be something that you want to pay attention to with publish subscribe scenarios, right? Now, excuse me. Now, what I've done here, I have another app, and I'm gonna run this show topic publisher, right? Now, my scenario that I have here is, again, I have another topic that I've created inside of Azure Service Bus running in the cloud. And I really created it because I want to know when different shows get created on these different platforms. So maybe Netflix has a new show, right? I might want to know about it. Me and multiple other folks might want to know about it. Or something comes up on Hulu or Disney Plus, or some new television provider has new content. I want to know when that happens. So I want to be able to subscribe to the messages that get created for those different things, right? So this is what this is simulating right now, is the creation of those different shows. Now, if I head back over, we'll close this, don't need that anymore. Now I'll head back over to my Azure Service Bus main instance, and under topics, you can see that I have a topic I created called shows, right? And so within a topic, I can create subscriptions, right? So subscriptions, again, being I want to, I care about a particular, message that's in here. So here you can see I have subscriptions for Disney Plus and Hulu and Netflix. If I click on the Disney Plus one, for instance, you can see here I have a filter. So I have a topic, my topic has a subscription, my subscription has a filter. And so this is saying, if you're listening to this subscription, right? This subscription only cares about things that have a special key with platform Disney Plus, right? So that means that the actual message, the actual AMQP message that's coming into Service Bus is going to have a special header, and that special header should be platform. And based on the value that's inside of that platform, I only want the ones that are here for Disney. And if we take a look at the other ones, I have Hulu and Netflix, and the similar thing is happening here, right? If I click on the Netflix, I should have a filter here, and this filter should be also here for platform Netflix, and the same with Hulu as well, right? Now what I can do, right? Like I'll come back over here. I've already published a bunch of messages. I'll actually stop this. And I want to show you how I can run multiple instances of the same processor. But now I'm just going to specify like which one of these topics, right, it should actually care about. Now, what I'm going to do, I'll run this in this thing called Docker Compose, right? And Docker Compose is really helpful because it's a little bit of an easier way for me to run lots of different containers and services at the same time. But what you'll notice here, if you're unfamiliar with Docker Compose, the only thing you need to know about is that, I have one service here. That's the generator. You just saw me run it, right? And then I have other services here, but notice that they're all show topic subscriber. So I have 3 show topic subscribers, but instead I have an environment variable that I'm assigning to each of these services. And the environment variable is very specific to the thing that they care about. So this one has an environment variable for Hulu, one has one for Netflix, and another one has one for Disney Plus. Okay. So I'm going to go ahead and pop this open really quick, and let's run this and see what happens. So now I should do a docker-compose -f, right? And I'm going to do docker compose -f, right? And now my compose file is the one that I'm looking at that has the pub sub stuff, right? Now it's going to spin up. Notice, see here, we go back to the top of this. So it started a processor for Netflix. It started a processor for Disney Plus. It also started a generator. But again, like you're just going to see this thing is just going to keep spinning and like doing stuff. One of the things I like to do is, when I have friends coming over and I want them to think I'm doing a lot of work, I just do Docker Compose and then here, oh, Cecil, look, what's all this stuff on your screen? It's going so fast. And it really makes them think like I'm doing a lot of hard work when all I did was run Docker Compose. But if we head back over here, if I keep refreshing this message, you'll just see, these message counts are just going to keep changing, right? But they'll keep changing because, again, I'm still publishing messages. But then each of these different workers that are, spinning across the screen are still there to work with them. One of the great things, too, I like about VS Code is that it also has a really interesting Docker extension that's here. And so if I wanted to, let's say I just wanted to stop the generator and I wanted to let the other things run, for instance, like I could right click this. I know this one here at the top is the generator because it says it. I could right click stop. And now the generator has stopped, but like now the other ones are going to go, right? And they're going to keep running until all of those messages that are inside of that queue are going to stop running, right? But, there you go, right? Like this is how we can do publish subscribe using something like Azure Service Bus and Docker. Okay. Now, the next thing I did want to talk to you about was that last scenario where we discussed sparse connectivity. Now, with a sparse connectivity scenario, we might have, again, like a queue that's running locally, but let's say I can't get to it for one reason or another. And so instead, I might want to have an intermediary queue that can help me with those types of messages. So I want to show you how we could do this with something like RabbitMQ. So you can imagine I have this Azure Service Bus running in the cloud, right? And this is just, a regular Azure Service Bus queue. Again, very similar to the other one. I haven't really done anything special to it. And then you can see that there's no messages in it at this point. Well, imagine now this is in the cloud, but I can't get to it at this point. What I could do now is set up something like RabbitMQ or AMQ. What I could do is set up something like RabbitMQ that's on my machine or within my local infrastructure that I could reliably get to, and set up a rule to have it forward messages over. And it turns out RabbitMQ has really good support for this using something called a shovel, right? So with a shovel, I can create a configuration that says, send to Azure, You can see I created one here already, but I'll just show you what this is like. Call this send to Azure, right? I can specify, the intake queue, right? The thing that I wanted to pull in from, and then the destination, right? And so now, like, I can send it to some queue that's inside of Azure, right? So the address of the queue in Azure would go here. And then this here would be like, the URI would be your Azure connection string. No, I already created one, and it's already existing here. So I'm not gonna dive into this really quickly, but all I did was just fill this out and it created this instance. And then also I do have a queue, if you can see this here, that says to Azure. So why don't we test this out? If you remember from before, I don't have any messages in that queue inside of Azure Service Bus, right? So if I want to say something like hello from the conference, right? That's going to be my message that I'm going to type in here. I'll send that one message, and maybe we'll send another one. I'm going to say hello from Florida because I'm in Florida right now. So I've just sent 2 messages, but those messages, I published them into this queue. But then if we scroll up, notice that the ready is 0. The total is 0, right? Like it took those messages and it sent them somewhere else. And now back here inside of my queue inside of Service Bus, I'll refresh. And there you go. You can see I have a queue count of 2, right? And I can check out the Service Bus Explorer that's here. I can click on receive. And then now when I hit this receive button, right, I'm able to look at this message that I got and notice it says here, hello from the conference, right? If I hit receive again, and I click on it, like hello from Florida, there you go. So there you can see, again, if I wanted to, all right, so there you see, if I wanted to, so there you can see, if we needed to have a situation where either my producer doesn't have direct access to the final destination queue, or I just wanted to add some extra resiliency, be able to send to one queue and have it forward to another in some creative pattern, I could do that using something like Shovel, or, there's tons of other projects that do this as well. Like Apache Cupid is another option. Or you could write your own code to do it yourself as well. But, again, there's already existing software and tools that can do that for you. So there you go. All right, so let's head back to the slides and let's round off what we talked about today. So we talked about different ways of communicating with our distributed systems, right? We looked at synchronous communication, and in that scenario, we have a sender and receiver. They both know where each other are, or at least the sender knows where the receiver is. And whenever the sender publishes a message or it sends a message, it's going to wait until that receiver is done doing that work, right? So that means that if the receiver takes 10 seconds or 5 seconds or 100 seconds, the sender is either going to wait for it or the connection might time out. But this is good for if you want to get like an immediate response or immediate feedback from whatever work it is that you're trying to send over. Asynchronous communication usually works alongside something like a broker. So we have senders, we have receivers, and then an intermediary, like a broker, a message broker, that's in the middle that is going to receive the messages from the sender, and then also, hold the messages for the receiver to pull out. So that means that whoever's publishing the message doesn't need to wait until the message is actually processed. It could send the message and go ahead and do whatever additional work it needs to do. And then if, needs be, like there could be a reply queue or even a dead letter queue that can happen, that can be pulled out whenever good or bad things may happen. But all depending on what you're trying to do, you may choose one form of communication versus the other. Another thing I want you to think about is, it's not like these things aren't mutually exclusive. You can use both synchronous and asynchronous communication inside of the application. And that's also very common. You might have something like an HTTP web request coming in on your front end, and then, having that create workflows in the background using message queues and whatnot in the background. That's totally fine too, right? And then using that with combinations of either proxies or different type of publish subscribe patterns to really create the type of environment that you need to be successful with your application. Now, if you're interested in some of the stuff that I talked about, hopefully you are, and hopefully you saw some good value out of what we talked about today. Head over to this address. It's theuralist.com, and This essentially contains this is a link of links, right? So if you go here, you'll see all the different links that I've collected that include both the code and docs and different types of samples that you could try out and learn a little bit more about some of these patterns that we talked about today. But, that being said, thank you so much. Again, my name is Cecil Phillip. Totally feel free to follow me on Twitter or reach out to me on LinkedIn if you wanted to. And I hope you enjoyed this session. Thank you.